All right. When you first start ColorForth, it loads this block, which, as you can see, defines a bunch of words in red that are just loads to load different applications. There's a dump utility, floppy disk interface, a thing to edit icons, to save. There's an audit utility for auditing changes that you've made to the code, PNG file generator, so you could take images in ColorForth and turn them into files that you can put on a web page. An HTML conversion utility, ASCII conversion utility, and these are just loaded initially when the system gets started. So there's a bunch of blocks that are loaded from source code to extend the ColorForth compiler with macros, compiled macros, utilities to decompress, native code dependencies, Windows code, native clock, timing, displaying the logo, format, anyway, all these little utilities that get added to your system when you first start it up. Then you're likely to compile as you need, soft sim or hard sim if you have the CAD package, or the IDE to talk to chips. And when you're writing code for the chips, it compiles code the same way hard sim does. And if we go up here to near the end of our blocks, we see target code. This is our target instruction set. Can you see that? Is that all on the screen there, or are we just a little off to one side? I guess I could adjust it, but I won't. And you can see these are very simple, just comming in opcode into an instruction slot. And here we define a bunch of target words, write down, up, IO, data, things like that. And we have instructions that require computation, like if, or dash if, or until, lit, for, begin. But they're very simple code for our target compiler. There are some small differences between target code and ColorForth code that runs on the Pentium. One of the differences is that on the target, next counts down past 0. On the Pentium, it counts down to 0. As a result, let's see if this is where I put this code. No, I put it somewhere else. Sorry. Let's try this one. No, that's not the code I was looking for either. Okay. Well, all right. Here is an example of a ColorForth program that defines a variable and defines a demo, and then has a word called demo in which it has a 10 for next loop. Just below that, we have a word called demo2, which has a 10 for next loop. But what it does is just increments a number on the stack. So if we compile this code, we just say 830 load. And now we've added that code to ColorForth. If we run the word demo2, we should expect it to put a 0 on the stack and increment it 10 times. Oops, I typed demo instead of demo2. If we type demo, we would expect it to increment my variable, my var, 10 times. Interestingly enough, you'll notice that when I do that, the screen updated. The screen's just showing you with this block, but the block shows you the definition of the variable. And many years ago, when we had variables in early Forth, like FigForth, you initialized the variable when you created it. You said something like 10 variable my variable, and it created a variable initialized to 10. In ANSI Forth, you don't initialize them when you create them. You say my variable, variable my variable. And then separately you say 10 my variable store to initialize it. And you need to initialize your variables somewhere in your program, and then your program is going to manipulate those variables. And when you restart the program, it's going to reinitialize them. Interestingly enough, when Colorforth does this sort of thing, it actually changes the value in the variable. And if you're looking at the source code, you see it change. You see it changing because it's a live display. There's a background display here. So this is a property we exploit in Colorforth. But my point was, if I type the word demo2, it leaves a 10 on the stack. Okay? Again, in other forths, you can do this also. You can open a window and specify you want a separate window to display memory contents, and you want to point to the variable called myVariable. And then when you update myVariable, the window which shows the contents of memory inside of myVariable will be updated. Well, that's sort of all built into Colorforth because of the live displays and the way variables work. Same thing with the stack. We have a live display here of what's on the stack while we're compiling, while programs are running, and so we can use that. But the point I was making is, for next with a 10 is going to execute 10 times in Pentium Colorforth, because that's kind of what Pentium wants to do. On the target chips, it's going to execute 11 times, because they're going to go through that loop one more time. So sometimes on the target chips, we use a word called ZIF. Now, I don't know where ZIF got its name. It isn't intuitive to me because it's sort of a backwards next. Next normally branches backwards to the beginning of the loop, but there's no reason it has to branch backwards. It can branch forward into your loop. So if you put a ZIF in front of a target loop with a 10, the first time through it's going to jump to the end of the loop, and you're really only going to get 9 times through the loop, or 10 times through the loop instead of 11 times through the loop. So sometimes we use ZIF in front of a for next loop. Another difference in the target and Colorforth is that in Colorforth, if you want to test a number or test something, for instance, we define a word called test. And we're going to take something on the stack, and we're going to consume it and make a decision. And what are we going to do with it? Well, let's compare it to 0. 0 or drop if then. And I'll put a semicolon in each clause. And that's the basic structure we would use in order to use an if. We would do our test to see if it is the same as 0, and then we would drop that result, because on the Pentium, the result is in a flag. So the if is actually testing the Pentium 0 flag. That's why after we compare what was on the stack to 0 and then drop that flag, we can still use an if with a clear stack. Yes? That OR is an XOR in Colorforth. That's right. XOR is used so commonly that we give it the shorter name in Colorforth. Again, right, it is an exclusive OR. But it is an exclusive OR on both the target and the Pentium Colorforth. So again, that's not a difference between the target, it's just a difference between Colorforth and other forths. The same with this thing here, where we're dropping the flag we just compared, and if is actually using the internal flag on the Pentium, just because this is written for the Pentium, so it approaches what the Pentium does a little differently than what Colorforth does when you're running it on the target chips. When you're writing code, I showed you how to simply set up a toggle loop that toggles a pin at a given rate. It's a very simple thing to do. But you may want to take advantage of the fact that we have code out there that's already been compiled for our ROMs. And because we don't have much memory, if you call the code that's in ROM, you can save space in RAM. And we have a whole list of routines that are in our ROM that are defined in high-level code: divide, fractional multiply, triangle, right shift, left shift, multiply, routing, taps for FIR filters and IIR filters. And I'm not going to go into how this code works or the details of how it was written. Some of it's very clever, very small stuff. Here's an example of how you would use taps if you wanted to set up a filter with 15 taps. 16 taps, right. Comment says 16 taps, 16 coefficients with intermediate storage interleaved. And basically you specify taps and you put in the parameters, and this calls that ROM code that we were just looking at, oops, right there, to do your 16 tap filter for you. There's a word to interpolate, which is very nice. Given a table of numbers and you specify the size and you take something and interpolate in between them. There's a polynomial approximation and an explanation of what it does. This is just a list of multiple port read and write addresses for when you want to read multiple ports or write multiple ports at the same time. And of course there's source code for the IDE and the SoftSim as well. But right now I just wanted to show you some of these nice routines that save you the trouble of having to write anything this small and effective yourself, because you can call these routines out of ROM. Fractional multiply, left shift, right shift, a triangle. Again, if you have questions about these, we should ask the authors, but there is code here to do trigonometric functions with very little code. In addition to these utility routines, which exist everywhere, especially where there's more memory, like on the central computers, we also have code that we boot. We have SerDes code, we have synchronous serial code, async, and you occasionally might want to call an async routine from inside of your program. If you didn't want to load an 18-bit word, but you wanted to load an 8-bit word instead, for instance, you go to the code for 18 bits and make a copy of it that loads 8 bits instead of 18. And then you call that. So again, you can call these routines that are in ROM to assist your code and make it smaller and more effective. Any questions? Yeah?
I have a question about the behavior of show and text versus mask. When it actually gets drawn on the screen, we call box.
And what's the question?
I've noticed that we call box and it's not immediate back. What's the relationship between drawing our thing on the screen or buffer?
Okay, well the only time where we draw boxes is on the logo and in OCAD, where we're drawing circuits. I could go show you the code, but we should probably go offline to do that. Okay, I got a fraction of a minute here. I just wanted to run one little thing if I could. See if I have that set up on here. Well, actually, I'll exit here and run an older version that uses different colors. And then I'll give up the stage here to someone else. And tell you what, I'll run this faster so you don't have to sit here and watch it go so slowly. Fast, go. And this program copies itself in 2 dimensions, passing along a bitmap, and then each node reads the bitmap and finds its location and what pixel it represents, and then it stays lit up if it's a on pixel or turns off if it's an off pixel. So I just wanted to show you Forth running on the machine. There you go. Just yank. It's not screwed in.